Hello everyone, we are Group 9 and today we'll be presenting our machine learning project.
For first baseline, we implemented a mixed stream CNN approach. The idea is simple. Instead of separating herbarium and field images, we combine them into one training stream. The baseline served as a reference point to see how fast CNN models can go without any domain adaptation methods, using direct 100 class classification. For the model design next, we used two architectures, ResNet 50 and EfficientNet V3. ResNet 50 used differential fine-tuning, where early layers are frozen and the final residual loops are trained, followed by a custom classifier head. EfficientNet V3 applies partial unfreezing of the last feature blocks with Adam W, level smoothing, and a cosine annealing scheduler for more stable optimization.
And now we'll show the code demo for baseline 1. After splitting the dataset into train and validation set, we apply the same data augmentation during training for both EfficientNet and ResNet model. For both models, the last few backbone blocks are unfrozen for fine-tuning, while the rest remain frozen. And the classifiers are replaced with a two-layer head with ReLU and a dropout for regularization. And for EfficientNet, Adam W with smaller learning rates for between layers, cross entropy with label smoothing, and a cosine annealing scheduler is used. And for ResNet 50, differential learning rates is used, where smaller for backbone, larger for classifier head. And Adam optimizer and reduce LR on plateau scheduler based on validation accuracy are used. And lastly, the result is showing overfitting.
Okay, so baseline 2 uses DenoV2 plant-specific features as fixed embeddings. We freeze the base model and resize inputs to 518 by 518 pixel and extract the 768-dimensional CLS token for each image. These embeddings are then classified using a 100-tree random forest and a standardized linear kernel SVM. We report top 1 and top 5 accuracy, including paired versus herbarium-only comparisons, and save all models for reproducibility. And this baseline tests how well shallow classifiers perform on frozen transformer features.
For the baseline tool, we basically just set up our environment and load the DenoV2 base model, which we reconfigure to extract deep plant-specific features. And these features are then used to train a random forest classifier capable of recognizing different species. To identify a new plant, we simply feed its image into the system, which is DenoV2, and it will extract its feature vector to the classifier to predict the species, and we instantly see the top matches. And for this one, it's basically the same. It's still DenoV2 to extract the features, but the only difference is we use SVM classifier, which uses the linear kernel function.
Moving on to the new approaches, the new approach A is a geometric solution with triplet margin loss. This approach uses a two-stage decoupling strategy. The first stage is feature learning. In stage 2, we freeze the backbone and trademark with classifiers either linear SVM or KNN directly on these embeddings for efficient classification. Finally, we use TTA averaging predictions from multiple augmentation views for more stable results. And for the feature learning in stage 1, after smart augmentation, we tune a LoRa-adapted DenoV2 model using triplet margin loss with semi-hard mining. This trains the backbone to produce a strong discriminative embedding space that separates species based on a visual similarity.
For new approach 1, we use metric learning on top of a LoRa-tuned DenoV2 backbone. We inject LoRa into the QKV attention layers while keeping the main DenoV2 weights frozen. We also add a small trainable head that outputs 256-dimensional embeddings, which are used for metric learning instead of direct classification. For metric learning and decoupled classification, we train the embeddings using triplet margin loss with a semi-hard miner to push similar species closer and different species further apart. Smart triplet sampler maintains class balance and prioritizes herbarium-only species. Once embeddings are extracted, we decouple classification by training linear SVC and also KNN directly on the embedding space. We apply test time augmentation by averaging predictions across 5 augmented views. With LoRa, metric learning, and TTA, the SVM reaches up to 75.82 top 1 on view images and strong top 5 performances as well. Overall, KNN performs slightly lower but still shows solid gains from the metric learning pipeline.
Approach B is a multitask model designed to bridge the domain gap. It focuses on what's constant, which is the plant structure, by learning domain-invariant attributes like leaf shape and arrangement alongside species. The architecture starts with a powerful frozen DenoV2 backbone. To make it adaptable, we inject trainable LoRa adapters into its attention layers. This gives the model the flexibility to learn our dataset's specific features without forgetting its powerful pre-trained knowledge. The backbone's feature vector is fed into 3 parallel heads, one for the main species task and 2 auxiliary heads that classify 5 leaf shapes and 4 arrangements, which helps the model to learn the plant's core domain-invariant structure. To train the network, we use this weighted loss function, which balances the main species task with guidance from our auxiliary heads. Specifically, we set the loss rates to 0.3 for both shape and arrangement and use the Adam W optimizer with a learning rate of 0.0001. Finally, we apply test time adaptation. We use the 10 crop method to generate 10 views from the crops and their flips and then average their probabilities. This makes our final prediction robust and insensitive to the photo-specific framing and orientation, providing the final boost to our accuracy. Our record demo begins with the baseline that validated our multitask concept. After generating our aligned DNOV2 features and LM-based labels, this code loads the pre-computed embeddings directly from a file. It then feeds them into this simple multi-head MLP classifier. This approach was fast and effective, giving us a solid starting point at 18.5% on the herbarium-only subset. Next, we upgraded to end-to-end training. This code uses GetPath model to inject trainable LoRa adapters into the backbone's attention layers. Despite making less than 1% of the parameters trainable, this was the game changer, doubling our accuracy on the unseen herbarium-only subset to 37%. Finally, we implemented test time adaptation. The code uses time crop to create 10 views and then averages their probabilities, which provided the final performance boost to 30.74%. Our final results confirm Approach B is the top performing model at 80.7% overall. It successfully solved the missing pair challenge, reaching 40.74% on the herbarium-only subset, where baselines scored under 4%. Our ablation study shows a clear progression. Morphology alone achieved 18.5%. Adding LoRa for domain adaptation was the critical step, doubling this to 37%. Test time adaptation then provided the final boost to 40.74%. In conclusion, our multitask learning plus LoRa model was a top performer. LoRa provided the critical domain adaptation, while multitask learning's guidance proved superior to metric learning and R baselines, successfully solving both the missing pairs and class imbalance challenges.
So now I'll be demonstrating the GUI. I have deployed our best performing model, the multitask learning model with LoRa and test time augmentation. So users can upload a few images and the system outputs both top 1 and top 5 predicted classes alongside the herbarium references images displayed in the rank order. To demonstrate the system, I have used a paired image found online, the Alamanda Caplatica L, as input, and the model correctly predicts the species, reflecting its 94% top 1 accuracy and display visually consistent top 5 herbarium matches. And for the species without pairs, the Crotalaria retusa L is used, and top 1 is less reliable, but the correct class still appears within the top 5, which has the 63% accuracy, highlighting the usefulness of top 5 retrieval for rare or data deficient species.
Thank you for listening.